Hi, my name is Nicholas Kotlinski, a data support specialist with the User Services team at the NASA National Snow and Ice Data Center's Distributed Active Archive Center in Boulder, Colorado. This presentation will give an overview of the IceFlow API and Jupyter notebooks that were created by developers and project teams at NSIDC in order to create a more harmonized data experience across the NASA ICESat, Operation IceBridge, and ICESat-2 missions. NASA Earth Science Research has long focused their airborne and satellite lasers on our planet's cryosphere in order to investigate why and how much our cryosphere is changing in a warming climate. Starting in 1993, the Airborne Topographic Mapper, or ATM, began collecting high-quality topographic information over the Greenland ice sheet and other locations through 2008. With the launch of the ICESat mission in 2003, NASA began collecting polar-specific satellite laser altimetry data using the glass LiDAR sensor, which collected data through 2009 and was decommissioned in 2010. Operation IceBridge flew from 2009 until 2019 and collected laser altimetry data with the ATM instrument to fill the gaps until the launch of ICESat-2 in September of 2018. ICESat-2 continues to collect laser altimetry data with its Atlas sensor. All of the data from across these missions are stored at the NSIDC DAC, and the wealth of data from these three missions, as well as from the earlier pre-IceBridge missions, presents an opportunity to measure the evolution of ice thickness, mass balance, and other measurements over several decades. However, combining data from these missions, as visualized in this animation, presented a challenge. This is where IceFlow gets to work pulling together information from across the entire time span of these missions. Data collected during the Operation IceBridge campaigns is stored in up to 7 different formats. ICESat and ICESat-2 data, on the other hand, were stored in HDF5. This mismatch means that data has traditionally needed to be harmonized or put into similar formats before comparisons could be made. A further complication is that the coordinate reference systems used to locate measurements have changed over time. To account for changes in the Earth's surface, terrestrial reference frames that relate to latitude and longitude to points on the Earth are updated on a regular basis. For example, since the launch of ICESat, the International Terrestrial Reference Frame has been updated 3 times. These changes in geolocation need to be reconciled if meaningful comparisons of measurements are to be made. IceFlow applies the necessary corrections and harmonizes the data for end users so that they can get to work faster. IceFlow uses a chain of services to provide harmonized point cloud data to users. The NASA Common Metadata Repository, or CMR, is a high-performance, continuously evolving metadata system that catalogs all data and services for NASA's Earth Observing System Data and Information System. This system makes programmatic search and discovery of data possible. IceFlow is built on a point cloud database of IceBridge, ATM, and ICESat global elevation data converted to HDF5 format. Finally, IcePix, a program developed during the University of Washington ICESat-2 Hack Week, is used to access and subset ICESat-2 data in HDF5 format through CMR and NSIDC services. IcePix is an open-source, community-driven effort that is continuing to grow and develop new and innovative ways to access and work with ICESat-2 data. The IceFlow API allows users to query, subset, and reformat a point cloud database in a form that looks very much like ICESat-2 data. This means no more working with multiple data formats, no more having to perform your own geophysical corrections, and no more having to perform your own spatial and temporal subsetting. The data is now harmonized and ready for time series analysis. While the IceFlow API allows for all data access and formatting options to be implemented in a terminal environment, NSIDC has also built several Jupyter notebooks for new users and those interested in viewing data before downloading it. Jupyter notebooks are open source web applications that allow users to create and share live code, visualizations, and narrative text in a single document. While the Jupyter project supports a number of programming languages, Python is the most common in the geosciences and the language used in the IceFlow notebooks. A binder link in the NSIDC GitHub page allows the notebooks to be opened in a fully executable environment, ready to be used by anyone. Several Jupyter notebooks currently allow IceFlow users to learn more about the project, access data through an interactive map widget, and format and visualize the data with pre-configured code. When we first launch the Binder instance, you'll see the Jupyter Notebook interface. You'll have the option to open several pre-configured notebooks, and here I'm opening the Introduction Notebook, which contains much of the information presented at the beginning of this video, but in more detail. In order to start accessing data, we need to first log into our NASA Earth Data account. To do this, we run the cell for NASA Earth Data credentials, provide our username, password, and associated email account. And then we set our credentials. Running the next cell will show that our credentials were accepted and that we are successfully logged into NASA Earth Data and NSIDC services. Once we're successfully logged into Earth Data, we can launch the IceFlow Map widget user interface. Here I'm doing so from the widget notebook. In the widget, we have a base map and can view IceBridge flight lines and ice velocity information from the Gibbs web service. We can select hemisphere information to change the map projection using south, north, or global projections. We can zoom into our map further, and using the polygon or rectangle selection tools, define an area of interest. This spatial information will be used to filter and subset data later in the process. We can then select multiple data sets from ICESat and IceBridge missions, and any desired corrections to the IceBridge ATM data can be made by selecting an alternative reference system and epoch. Next, we have the choice of selecting ICESat-2 data products from those products most related to land and sea ice. These will be spatially and temporally subset based on our parameter specifications. And finally, we can choose our time frame of interest to further filter the data. Map widget selection parameters are automatically passed to a parameter variable in the notebook. Here I'm selecting IceBridge and IceSat products, and we can use the designated widget buttons to view the raw unsubsetted granule count from CMR and print the current parameters to make sure all of our download parameter settings are correct. You'll need to open a log window to view these outputs. We can also do this programmatically in the notebook to see inline outputs from both the build parameter function and the query CMR function. Here we'll query CMR for IceSat class and IceSat-2 ATL06 data using predefined parameters. This query returns the approximate download size of each product, which may differ from the true size of data after spatial subsetting. We can then place our data order in the following cell. We can then check the status of our order by running the next cell, in which case we should get a message of in progress, pending, or complete. During this process, you will also receive an email for your submitted and completed data orders. First, the ICESat-2 data is retrieved using the IceFix API. Any IceSat or IceBridge data will be returned from IceFlow as a single formatted granule once the IceSat-2 data has been received. IceSat-2 data is delivered separately and in their original format, which is already optimized for comparison with IceFlow point cloud data. As our order is completed, we can open it in our data folder, where it can be opened and merged for analysis within the Jupyter notebook. Here we're using the data visualization notebook to organize some pre-downloaded ICESat data into a usable data frame. We can load the data using the h5py Python package, and using the IceFlow Common Data Frame Dictionary, we'll have an organized data frame output with common column names such as longitude, latitude, and elevation across datasets. Then we can use the Vex package to downsample larger data frames for quicker visualizations later on. Here we can look at some plots from the IceFlow Data Visualization Notebook. The first plot gives us a simple two-dimensional map view of IceBridge ATM data over the Thwaites Glacier in Antarctica. and we can zoom in for more detail. The next plot shows the same data, but as a three-dimensional point cloud. And we can see the data change interactively as we move along the flight line using the slider widget. This and other visualizations are available in the Jupyter Notebook, and the harmonized nature of the data in the IceFlow database makes these types of interactive visualizations easy to program on your own. Thank you for watching this overview of the IceFlow API. You can access the IceFlow Jupyter Notebooks and learn more about the API on our Data Tutorials GitHub page, or by visiting the ICESat, ICESat-2, or IceBridge dataset landing pages on nsidc.org. You can also email NSIDC user services with any questions.